Greetings Dr. Chen and everyone watching this. We are from Group 13 for KIB1011 and our group topic is Enhancing Surgical Stapler Performance, a study of statics and material mechanics. My name is Noreen Yasmin binti Nizam, matrix number 24068637-1.
Hello, my name is Nursan Ade Malayo and my matric number is 231-21111.
I'm Nabila Izzatiluda Putri binti Muhammad, matrix number 24068744-1. Let's start with the introduction. There's many types of surgical stapler, such as skin stapler, laparoscopic stapler, and vascular stapler. These staplers serve different functions according to their surgical procedures. In this study, we are going to talk about a specific type of laparoscopic stapler. The endo-GI stapler, which stands for endovascular gastrointestinal anastomosis stapler. It is commonly used in multiple types of surgery, such as gastrointestinal, bariatric, thoracic, gynecological, and urological. It is designed for precise cutting and stapling of tissues, although it has been associated with occasional malfunctions, such as failure to fire, misfiring, and improper deployment of staples. We investigated a case report from the Journal of Surgical Case Reports from the year 2018 on a case involving endo-GI stapler malfunctions during a surgery.
From what we have obtained from the literature review, the patient was a 72-year-old man with hypertension, chronic kidney disease, and other comorbidities. He came to the emergency department with abdominal pain and was diagnosed with ruptured appendicitis, peritonitis, and sepsis. An emergency exploratory laparotomy was performed, including an ileocecotomy, appendectomy, abscess drainage, and ileostomy. During the surgery, the terminal ileum and cecum were successfully transected using endo-GI stapler. A few days later, the patient developed a complication, a dehiscence of the staple line in the ascending colon. As a result, the team had to perform a second surgery. Initially, they attempted to use endo-GI stapler to transect the ascending colon. However, the stapler malfunctioned during the procedure. Specifically, it froze, emitted a sound, and locked mid-operation. Despite efforts to resolve the issue, manual override attempts failed. Consequently, it took 10 minutes to separate the stapler from the tissue. Afterward, the team decided to switch to a contour stapler, which they used to complete the transaction successfully. As a result of the malfunction, the patient's recovery became more complicated. Notably, he experienced several issues including recurrent fecal peritonitis. In addition, he had high ileostomy output which required IV hydration. Moreover, delayed wound healing occurred due to sepsis. Despite the significant challenges, the patient was eventually discharged to a nursing facility after 8 weeks. Let us now discuss the implication of this case. This case clearly highlights the risks associated with stapler malfunctions. Although these incidents are rare, they can significantly prolong surgeries and worsen patient outcomes. Therefore, it is crucial for surgeons to be prepared and manage such situations efficiently to avoid further complications. In addition, ongoing training and research play an essential role in improving the safety of staplers and refining troubleshooting techniques.
Now, let's take a look at the objectives of our study. We aim to investigate the mechanical failure modes of endo-GI stapler to analyze causes of malfunctions in the fire mechanism during surgical operations based on statics and mechanics of materials principle. We also target to achieve these learning outcomes. First, use free body diagram to perform equilibrium-based analysis for various structure. 2. Solve problems involving a body under the action of axial bending and torsional load. 3. Employ moment and inertia-based analysis for problem solving due to compound load. 4. Evaluate stress and deformation of biomedical devices. And last, perform effectively as a team in analyzing real-life cases of static objects under loading.
So I'm going to talk about methodology and calculations. Starting with the free body diagram. In the equilibrium analysis, we use the free body diagram to analyze the equilibrium of forces during the firing process. The primary forces considered were Fa is trigger force equal to 200 Newton, Ff is internal resistance equal to 10 Newton, R is tissue reaction force equal to 240 Newton. Here is the equilibrium shown on the slide where all the forces equal to 0. This analysis helps us identify force imbalances or misaligned forces that could lead to improper staple deployment, a common malfunction in the staple firing process. Next, we have axial bending and torsional load analysis. Here is the calculations shown on the screen. Using axial load on the firing pin, bending load on the staples, and torsional load on the drive shaft. These calculations illustrate how mismanagement of loads could lead to mechanical failure, such as jamming or misfiring. Third is moment and inertia analysis for compound loads. We analyze compound loading conditions using principal stress formula shown in the screen, and the result is 408.59 megapascals. This analysis helps us pinpoint critical stress areas in the staple mechanism, allowing for targeted design improvements. Lastly, we use stress and deformations analysis. We evaluate stress and deformation in the stapler's components under different loading conditions: axial deformation of the firing pin and bending deformation of staples. However, for bending, minimal deformation was observed, underscoring the importance of material properties in resisting bending stresses. Through this, we identified areas where material improvements could enhance the stapler's reliability.
Surgical stapler is subject to mechanical and operational stresses that may lead to failure, akin to any other medical devices. One of the problems is excessive application of axial force during firing, caused by uneven distribution of forces upon the staple, which leads to misalignment. To solve this problem, we can optimize the stapler's design by using stronger alloys like titanium to ensure the device's ability to handle axial loads. Another possible drawback is during firing, staples might get bent or misaligned, causing incomplete staple formation, hence poor tissue approximation. The solution to this problem is to use stiffer material for staple to increase the resistance to bending and then improve the alignment mechanisms within the stapler.
To conclude our analysis of the endo-GIE surgical stapler, we focus on its mechanical performance, particularly the firing mechanism, and identified key issues like excessive axial loading, malformed staples, torsional stresses, and insufficient tissue compression. These factors can lead to a device malfunctions. Using principles of statics and mechanics of materials, we analyze forces through free body diagram and investigate axial, bending, and torsional loads to pinpoint failure points. We also conducted stress and deformation analysis to understand the stapler's limitations. From this, we propose solutions including material improvements, better alignment mechanism, and optimized designs. Our findings support the hypothesis that load distribution, alignment, and material weaknesses are primary contributors to failure. Addressing these challenges is crucial for enhancing the stapler's reliability and performance, ultimately improving patient outcomes. And that is all from us, Group 13. Thank you for listening.
And in the end, here's our references we use in this assignment. Thank you for listening.